Okay, afternoon, everyone. My name is Jędrzej Osinski, and the talk is the future of software development. First of all, I would like you to forget for a moment about all your issues you are working every day, about all the bugs raised recently, and focus on the so-called big picture. So how the IT will evolve, and what's the future in front of us. And that's what we focus most in this presentation. So no low-level details, actually no source code shown, maybe the only presentation like that. But I hope it will be inspiring and you found it interesting. And if you just for a while think after the talk about what's the future and what's my place in that future, it will be my success. Okay. Oh, sorry. So the main scope is I will say just a few words about myself. Then we've discussed about the topic I called black box. We'll see more details soon. Then about artificial intelligence itself. Then about AlphaGo, its success and all the consequences that are behind it. And finally, we look at the signs that are around us, which we maybe not notice at the first time, but they are suggested what the future may be. Not too much about myself, just I'm 6 years in IT, so I've been working as a developer, tester, I'm also line manager. On the other hand, I'm 9 years in science. I've got a Ph.D. in artificial intelligence, giving lectures at Poznań University. So I'm also a university teacher. And this kind of unique experience makes me always think to the boundary line, where the science meets IT and IT meets science. So that's not my first talk around artificial intelligence and some applications in IT. I just always try to look how much science is what we actually do every day. So that's a nice question for you as well. So first, the black box. Before I define the black box itself, we'll discuss how the terrorists change, what's actually this black box. I will take you for a very brief time travel, and finally we will check that the black box is in each and every of us. So I would like to start from this Karl Popper, who work a lot around the topic of the philosophy of science, so how it happens that theories appears, how they evolve, and he also wondering when it's possible for a new theory to replace the old one. I mean, assuming that both are of course correct, but we have new theories, so the only chance for a new theory to replace the old one is to be either more general or more precise or more simple. And if we think on any development tool, any programming language we encounter every day, the reason why it's get popular is that it's one of these applications. I think you agree with me. So it's not only theories, it's actually one-to-one in IT as well. So the programs which are simple to use, cover more of cases, are easier to implement, these languages are more and more popular. So now about this black box. So let's define it just for the purposes of for this presentation. I will say about black box if there is something we don't know or we don't understand, like we don't know how this application is built or we don't understand how the specific algorithm works. It may be also something we cannot see. So if we are a final user, we are unable to see the source code. So it's also a black box for us. And finally, the source code, the black box can be something that we don't really care. I mean, we implement a lot on the high level, and actually, how many of you really care about the low-level hardware details? Anyone? Yeah, so just a few people. So I mean, it does not mean that we don't understand it. It just might mean that we don't really care. So this time travel. So if you look how it was changing for the last 70 years, that's this, one of the first computers, the Turing one. Recently you can see in these few Hollywood movies also. So actually there was no black box. I mean, the Turing was able to see any particular element moving, and he was able to modify it simply, modifying bots, simply modifying the hardware. So there was nothing hidden there. But if you look a little bit later, when assembler came, assembler is already a very small but still a black box. Can you see this? So it's like we have some commands like add AX and BX, but we don't really care now what's happening behind. I mean, we can learn how it works, but we don't need it. The black box is becoming bigger, right? We've got this Fortran, if-else statements. We've got the C, like around 1970s. So we have like statements like declarations, and, variables, etc. And we produce the whole applications. What's next? Classes. Like we sometimes don't really need to look. I mean, the classes as another structure of the code. Then we have Java, which also gives us extra garbage collector and many other things. There was a few presentations about Java, so it's you can learn a lot around this. But then the first one was also contains much bigger black box than the C++ itself. Then we have look more on the classes. So we work on the classes instead of the code itself. So it's like we use quicksort, but we don't really need to know what's behind it. Yes, how it really works. We just use it. Then packages. So like we use database interface. How many of you use it like every day, or maybe use it at all? Yeah, it's like standard way. Yeah. So, but we don't really need to look too much in it. I mean, in general, because of course some people need, but it's like a general way the world is changing. Then we have got these libraries which are even bigger. So like, let's use vector graphics. Okay, here you are. Then we have components, like a whole component with the following parameters. Like, everyone is working on components nowadays? Anyone can raise a hand? So then we have what we have now. We've got core frameworks, so we are able to create the whole site with many pages just with a few clicks and a few comments, right? So that's the current state of art, let's say. What the future will be? If we can imagine this growing up black box, we can say that, okay, the next step will be probably test-driven auto development, right? I haven't put the date. It's like difficult to estimate, but still it's the future, it's not so far. So we have test scripts, great. But if the test scripts are written well, why not allow them to create a little bit software, like automated test-driven development, right? It's already happened, but with our hands. But it may be sooner or later automated, like neural networks, etc. Well, what will come next? Probably auto development based on requirements. Of course, well written, well defined, but still not necessary in the source code style. Okay, what will come next? Again, I didn't give any date, right? I mean, that's a kind of prediction we can conclude from how this was changing before. So again, we'll just provide some ideas. And the final step, from our perspective of developers, because it was unfortunately ends a little bit our let's say job positions, will be the strong artificial intelligence, right? Which will work without any requests, will generate something that could be nice or bad, and we'll discuss about this later on. Yeah, so the conclusion is the world is changing. This black box is getting bigger. So, and this perfectly matches this idea by Popper. Yeah, so everything is get simpler, more general, and our own activities are more and more limited. It can be scary, but it can also be an opportunity. Okay, so now let's have a quiz, just to check how big your black box is. So I would like to ask you to raise hands for people when I'll be asking. So how many of you knows what's the main difference between HTTP and HTTPS? Okay, keep your hands up if you also know how the SSL protocol works. At least generally, don't need too many details. Okay, let's keep hands up if you know how the RSA system, which is behind that, works. Okay? Keep your hands up if you know the Fermat-Little theorem, which is based on. So you can at least say what's the key of this theory and just rephrase it yourself. Cool. Who can prove it right now? Okay, so that's a nice case. I mean, because it shows that actually this black box is everywhere. So it's like on the screen. Don't feel disappointed. Black box is a natural way our brain works. So we need to assume some foundation to build a skyscraper, right? So it's like, it's quite normal. We don't understand everything behind. The key for us is just to remember that there's this black box is always there, right? Okay. Now we'll talk a little about the artificial intelligence itself, and we'll probably mention this black box a few times. So we talk about what's the difference between weak and strong artificial intelligence. Any of you know the difference? Okay. So we'll see that weak artificial intelligence is actually all around. Anyone knows that? We'll check what's the Turing test. We'll say what Aquarium metaphor is. I think it's opposite sequence, but doesn't matter. We'll say what's actually the singularity. And we'll look how this IT evolution looks like, or will be, or would be. Okay, so the main difference is weak artificial intelligence emulates a single competence of human. Like, single competence could be like ability to recognize letters, right? So this all of these OCR systems. Single sense can be smell detection, smoke detection, etc. Single problem can be a game of chess, right? We've got computers that can play chess, play Go, play StarCraft. Yeah, so it's like normal. So actually, every time you say about something, mention it as artificial intelligence, you really mean about this weak artificial intelligence. As the strong one does not exist yet. So the strong one would be the one that has all the competences, human competences, that is able to resolve any problem, for example, a Turing test, that is characterized by consciousness, by feelings, self-awareness. This one is quite interesting. I mean, because as you can see, they a little bit influence each other. Like, if it's self-aware, so is it possible for a computer to recognize, identify itself among the crowd, in the cloud? And if so, can it get some feelings like a fear of death, for example? Okay, if I know that it exists, that should be a natural consequence, yeah? That I may be afraid that I will stop existing at some point. So these topics a little bit, sorry. I'm not sure, can you see this? Okay, so these topics can influence each other. And finally, creativity. And someone may arise that, okay, we've got this genetic algorithm, but still it's not a kind of spontaneous creativity, right? It's like we give the fitness function, we say, okay, what's good, what's bad. By creativity in here, I mean this spontaneous creativity. The computer creates something just because wants to do it. Okay. Okay, now about this artificial intelligence around us, the weak one, right? So actually, whenever you type or swipe your mobile, you're actually touching artificial intelligence. All these algorithms that detect your touch are based on this artificial intelligence algorithm. That is because everyone touches differently. Everyone touch a little bit, not the same place. It would be impossible to implement such a behavior without artificial intelligence we have now. So, like, actually, if you have a mobile phone with you, the smartphone especially, there are probably dozens of algorithms based on artificial intelligence in there. We just don't. It's just a kind of black box for us. It is also used for this kind of mathematical calculations, like identification DNA sequences. It's also used in the automobile engineering a lot. For example, this ABS brake systems are also based on artificial intelligence, which is not maybe a common knowledge, but it may be scary a little. Right? Even more scary will be this one. So I'm not sure if you know that, but fuzzy sets, so a part of artificial intelligence, is used to control the security of nuclear plants. So actually, we already give our security to artificial intelligence. Still the weak one, but we already did. Artificial intelligence also help us to look for some underground resources, like gas. It is also used to control our traffic lights. In games, it's probably the one that is the most visible for everyone, right? We just play against the computer. It's sometimes not so easy to win. Also in telecommunication, even autofocus in your camera, it's also based on this kind of algorithm. And finally, even your kitchen is not free from artificial intelligence. Most of the modern devices which are eco-friendly, they are using artificial intelligence inside, like fridges. Scared? Anyone scared? Don't worry, guys. Okay. Now I would like to share with you a few thoughts about this algorithm we already have. So, any one of you knows how the neural networks, artificial one, works? Okay, like a quarter or closer to half. So I will say just a few words. I'm not going to go into the details. Generally, it's like artificial neural networks are inspired by the neural networks that are inside our brain, right? So a single neuron in our brain does not change anything. I mean, I'm not sure if you know that, but every day, a few hundreds of them die, and we are not feeling much dumper than the day before, right? So actually, the power is in the amount, right? And the relations and connections between these neurons. So the same way works the computer. A simple neuron is just a kind of if statement. I mean, the simplest possible case. So if the sum of the incoming signal is higher than some value, then the output is 1, otherwise it's 0. And the wages for each of the connection is calculated using different algorithms. So simply speaking, we give some data to neural network, let it to learn, and we show, but how it's going to learn, we just show it that for this particular data, the expected value is this one. For this particular data, the expected value is this one, etc. So after thousands, hundreds of thousands cases, the neural networks learn this kind of sequence or this kind of data, and if you provide something new, the neural network is able to answer correctly which category it is. That's the main idea. What's important in there? So we've got, for example, the one is one of the outputs, right? So actually, we can try to trace it back a little, like, okay, what was the values before that makes it one? But actually, if we have few thousand layers of neural networks and hundreds of thousands of neurons itself, it's actually become more and more difficult, and we actually really are unable to find the case, I mean, the cause of actually one being in here. Nobody really invests in searching for such information. What we do is we just give another data to make it learn better, to not to make this mistake anymore, right? But what's interesting in there, we don't really know what's happening inside, like in our brain. So actually, believe me or not, but we can treat it a little bit like a black box, even nowadays, not the future. Even today, we are not really able to interpret correctly a specific output of a neural network, right? We work with this like with a living organism, actually. So, okay, you are making a mistake. I'll give you another data. Just keep learning, and you'll be better. We don't invest in changing a little bit value manually for a specific connection, right? So it's quite interesting. Similarly, if you think about this genetic algorithm, how many of you have ever touched it, know how it works? Okay, so just a few words of introduction again. So the idea is you want to generate something, whatever it is, a kind of data that meets some specific purpose. So we start from random data, and then we work like a biological population works itself. So we select the best. So we have a random population, which is can be a sequence of bytes, sequences of bytes. And then for each of them, we just analyze whether they are good enough or not. If not, we just remove them. And the winning one, we cross over. So we mix them, like the beginning of the first sequence with the end of this other sequence. So then we add a little bit mutation, so just a random changing of bits. And that's how the new population is to be generated. And we have sequence of sequence of sequence, like the evolution works. That's why it works, evolutionary algorithm. Yeah, so we just have some random input, then we show what's actually good and bad. I mean, whether a specific sequence fits our expectations. And finally, we get the thing we would like to produce. So if you look more closely, there's also random. It's not only at the beginning, but also in the middle. Like when we cross over different chromosomes, how we used to call it, all these values, we are not always doing it the same way. Then we mutate it. So for example, we change random 1 to 0 or vice versa. So if someone told you, like, why exactly in the population number, like this, the item number, this one, is actually looks like this, we are again actually unable to answer this. also because of these random aspects that appear in the meantime. So again, actually, the black box is already there. I mean, we generate something, we are happy about the results, but we don't really trace it back. I mean, if we had to, for example, this technique is used to design antennas for the spacecraft, so they have a very strange shape, which is designed by the algorithm like this. But if we want to design another antenna, we are not trying to understand how it works. We just use this algorithm to do it again. So it's quite interesting, as it seems like we still don't know how to do it well. We just ask the artificial intelligence to do it again. So it's quite amazing if you think about this a little bit more. So we already we already trust a lot in this algorithm. Now, how about this aquarium metaphor? Anyone heard of this? It's quite rare, so I'm not surprised, actually. The aquarium metaphor is like we have two people being in this big aquarium and standing in this awesome, huge glass wall and watching this fish swimming there, right? And these two people, and I think everyone agrees with me, are able to discuss each other like any particular fish they like. Like, look at this fish. This is good. It's very nice. It's so colorful, right? I think it's like no problems in that for everyday life for us as people. But from the computer perspective, it's quite amazing problem. Like the data is not precise. Yeah? We don't have any measurement tools. We just look. The environment is fuzzy, and it's also dynamic. The fish moves very fast. Finally, we have a kind of relative perception. Like everyone has a different experience, different color recognition, and also stand a little bit in different positions. So a particular fish can be like hidden behind the rock, like for one person, and visible to other, right? But still, they are able to discuss any topic they like. And actually, it's impossible for a computer. So it's also kind of interesting, because sometimes we said, okay, we are so clumsy, we are so imprecise, we are so subjective. We are use feelings that are not objective enough. And actually, if you look at from the perspective of this metaphor, it's our strength, right? This being imprecise, being relative, being fuzzy a little bit. So that's what we actually very often perceive as our weakness, is our strength, and that's what allows us to survive in the everyday environment. There are just too many data around us to analyze it well, right? So that's what's challenge for the computer. So something what is our weakness is our strength over the machines. About Turing test, anyone heard? Yeah, it's quite popular. So the idea is how to check that we have created a real strong artificial intelligence, actually. So we need to check whether it's able to discuss any topic, and we are not actually able to recognize it from a human being. So the idea is we have a kind of wall, whatever it is, and we have a set of machine entities and real people, and then we have the testers who may talk to the other interlocutor, whoever it is, and he doesn't know who it is, and for each decide whether it's human or a machine, right? And that's a kind of statistics, yeah. If we are actually statistically unable to recognize whether I talk to a machine, or I talk to a human, then actually the machine, the artificial intelligence, passed the Turing test. What's also interesting, it was like described in 1950, and it's still open task, right? So no machine is really able to imitate human way of discussing. I mean, how do I know what?
How do you recognize if there is a machine that imitates human so well?
Okay, nobody ever announced the actually result of passing Turing test yet, so that's maybe the key. But what you mean probably is that maybe there is already there somewhere hidden, right? Nobody knows. Okay, this is clear. Yeah, I think it's interesting and still open task. I think there are some money to be given to a person or the team who is able to do it, but probably the work is much more cost consuming than the further hour anyway. Okay. And now I wanted to show you some interesting graph from this from Wikipedia. And actually, if you look at this, that's a kind of you can see there's like years, and we have these blue boxes are the error rate of artificial intelligence in machine classification of images. So we have some images, like, and how well these machines are able to recognize it. Right? But what is really interesting, and of course this it's getting slower and slower as we could expect. Yeah? The algorithms are better and better. But what is really kind of amazing is the red line is the error rate of a trained people. So, and look at the last year. And it's last year, not the current one. So actually the red line is above. So we are already at the moment in our history we can start asking the question, are we able to verify the computer output yet? Can you see this? If it already recognizes images better than ourselves, how are we able to verify whether the results are correct? We only can trust it. So we have no other option. A little bit scary, but maybe exciting as well. So yeah, so if you look at the picture before and we look at this, whatever the IQ mean, I mean, it's not a definition. I don't want to follow any definitions, like more ability to learn, understand our knowledge, like a collective component. So actually, as we develop ourselves as a humanity, this line is growing up. That's a kind of obvious. But we can imagine the moment when appears something which is called singularity sometimes, in a little bit more like science fiction, but I would prefer saying futuristic. So the singularity is the moment where the computers will be able to learn itself, like one another or in the cloud. And later in this presentation, you will see that it's really not far away from. So suppose the computer at a specific moment achieves the ability to learn itself, so they are on the same level as we are. As they are computers and they work in the clouds, and they have access to all the data, we cannot expect anything else than going it up much faster than we do. And actually, what about us then? So I believe there's only two paths we can go. Like, either we start learn from machines, so it's a little bit change in the history cycle. Like we are teaching the machines, but in the future we may need to learn from machines. And if we do it effectively, will develop ourselves much faster than we would without the machines, right? The other scenario is like we just don't care. Like, okay, machines do anything anyway. I mean, we have all this illness cured already. We have all this stuff produced for free on our Earth. Actually, we don't need to learn and develop. Why? We cannot invent anything faster than the machine themselves, right? So how many of you think we would go into part 1? And in part 2? You need annual leaves, guys. Have a break in your job. Okay. Okay, so that's the 2 scenarios we can go. And how about the IT evolution itself? If you look at this, when I was preparing this slide, I was imagining a huge scream from the audience, like, no, it's not possible, never. I mean, I'm still like algorithms. Why it says I'm not doing it now? So okay, it's not about everyone. Yes, that's how I perceive the tendency, the mainstreams, let's say. So at the beginning, the mathematics was key. Like, actually, computer science were mathematicians, sorry, who just also work with the machines. Like, that's why the computer is called computer, right? Computational machine. Nowadays, how many of you use mathematics in everyday work? Yes, so that's what I mean in this diagram. So hardware complexity algorithms, they're also a little bit left by us to someone else. Someone is doing it well. Let him prepare an algorithm which is like works fast, and I will just use it, right? Actually, we are starting the area when we are touching the code even less. I mean, generally as the whole IT community, maybe not people in here, as this typical developers conference, but that's the mainstream, right? We look more to patterns, like how many of you focus on these good practices or patterns you found somewhere, right? So we are not really developing them again, right? You just reuse them, and it's nice. What comes next? Configs. It's already almost there, right? How many of you spend half of your time on configuration, Jenkins, Maven, and everything else? Exactly. You see that? How many of you works in support? So just support, are they your colleagues or your client, or, yeah. How many of you do it like in half of your time? Okay. So that's the key, yeah? We move more to consultancy, to user experience. Actually, if we think about the world, 10 years ago, nobody really ever nobody was really thinking about user experience. Come on, it needs to work. Why we need to have it work nicely and be pretty or be beautiful, right? Now it's the key. And the power of this will be even increasing, right? We have a whole conference only about user experience. We've got professional user experience testers. We involve tools to do it, right? It's something we were unable to imagine 5-7 years ago. And it's getting stronger as the code itself will be a little bit behind. So the singularity, this self-developing machines, we can give them a very nice input as a UX. Then we'll unfortunately will be left only to test what they actually do. Yeah? So don't be sad. I mean, it's not so near future. I hope we will have time to get retired before it happens. But we need to prepare the next generation that writing the code using debugger is something that they watch only in the movies. Right? So testing, yeah, we will be testing what actually machine does. We'll do. Then train. So train people who are less familiar with IT than we are. And the last step in this journey will be just we'll all become users. I mean, that's actually almost sure future. The unsure aspect is to when it really arrives. So, how to postpone unemployment? Do not act automatically. Okay? Try to avoid checklists and scripts. I mean, if you are following checklists all your day, it means sooner or later you can be repeated by a machine, which will do the same and have less chance to make a mistake. So be careful. Break stereotypes. So work independently. Think about more general. Cross standards. Develop your own patterns. Try to do it. Maybe you find something more better than it is now. Use creativity. Follow intuition, the thing that machine we are not sure will ever have. Okay, now a few words about the AlphaGo and why it's so amazing. Why actually the whole scientific world hold their breath when they heard about this, and it was like, you know, published on the cover of the Science or Nature magazine. So a few words about Deep Blue. We'll learn what's the difference between Go and chess, because that's the key. We'll look what was the AlphaGo strategy, and we think about how much we really understand. So whenever I say about this to people who are not in IT too much, like from other areas of our life, they always ask me, okay, how it's possible it took 20 years for AlphaGo to win with the champion, while Deep Blue won over the Kasparov in 1997. Yeah, 20 years. So the answer is inside the rules of these games. So maybe a few words about the Deep Blue. So its strategy was mostly based on brute force computer power. Right? Those 30 nodes, 120 megahertz each, gigaflops 11. I read that it was actually in the 700 most powerful computers on Earth at the time. So it's a really strong machine. So having such a power, it was able to calculate 200 million chess positions per second. And what's even more important, it was able to search to a deep of 6 to 8 moves, and in some cases even 12. So that's something that even Kasparov was unable to follow. And also there are 700,000 Grandmaster games on disks, which are also used to check for inspiration before the move is done. So the disks were also very big, and they were even replaced during the match, which was one of the Kasparov's arguments it was one of his arguments that he really didn't lose the match, yes, because the computer was changing during the match. It was just too big to have it all connected at the same time. So mostly brute force. Now, what's about this game of Go? Anyone plays Go in here? Cool. Origin China, 5,500 years ago. And what are the rules? That's actually the Go board. What's actually the rules? The rules are very simple. You need to get more territory than your opponent, following these two simple rules. So stones that are surrounded by your opponent are removed from the board, and the position of a stone cannot be repeated. So if the stone is removed, we cannot put the stone again in the next move. So that's all the rules, right? So simple. But it's paradoxically, if it's simple for human, it's very difficult for a machine. Why? If you look at the chess, we have 400 configs of the first two moves, right? Each piece has its own style of moving. It's also very, very specific. There are complicated rules like casting and pass and promotion check. It's something we don't find in Go. What's actually the key? The good player is a player who has a very good memory. So he can learn from the previous games with other opponents. So he knows that the sequence of moves like this can lead to a success. And of course, mathematical skills. On the other hand, what's the goal? That's 129,000 possibilities for first two moves. If we imagine all the possible games that can be played, it's 10 to the power of 1,000. So if you think about computers, even the faster computers today are unable to analyze everything the way the Deep Blue did, so by brute force. Like, that's the key. So the key is imagination in this game and the ability to analyze the situation globally. So sometimes we call it like a big picture helicopter view, right? So that's actually the things that are important for a Go player. So as you can see, like brute force is useless, especially because of this and this. So how actually the AlphaGo works? So first they learn it to predict the next move of its opponent, right? Based on many master games, it was like artificial intelligence learning. What's actually interesting in here is they didn't want it even to have it like 100% result, right? It was enough to achieve it in the 57% of cases. So a little bit above, in the 57% of cases. So not even more needed. So what was done next, and that's also awesome. So the AlphaGo instances were distributed in the cloud and allowed to play each other, to learn, play better. So when I told you a few slides before about singularity, and you look at this image, where the AlphaGo is learning from itself just by playing against its own instances, you can see it's not really far away, right? Because what's really, if you think about this more like philosophically, let's say, actually we are unable really now to assess how strong the AlphaGo is. If it's better than the best among humans, and it will continue playing against itself, we are actually lost, right? We don't know really how strong it is. So that's another diagram I just prepared, and I hope it will be inspiring. So if we think about the skills we have, and the skills that artificial intelligence have now and in the future, we can draw a line and say, okay, everything below is something that we are able to do, right? We can do it, like playing chess or something. The AlphaGo is a little bit above this line. So actually, we are unable to play as well as AlphaGo, but at least we know how it works, right? And when I draw this part of the diagram, then I imagine that this is not the end, actually. You think there will be something more? I think the next step that is in front of us is we don't know how it works, but we know what it does. Yes? In the case of AlphaGo, we know how the algorithm works. In the future, when the computers will develop itself, we'll probably stop understanding at some point how this algorithm really works. We'll be able only to understand what it actually does. Next level. We don't know what, but we know why it's done. Right? We know the purpose, but we don't really know how the AI wants to achieve it. And what do you think? What will be the top level? Okay, AI is doing something. Actually, we don't know how it's doing. We don't even know what it is doing. And unfortunately, we don't even know why it is doing this. So that's a kind of scary. Okay, 8 minutes left. So about the signs that are around us. So I will tell you a few things about this stuff, and what's important, all of these things happens in the last year. So that's a kind of thing that should work on our imagination. First, we have this open letter during this artificial intelligence conference. That was the idea was just to ask for banning using autonomous weapon based on artificial intelligence. If you look at these quotations, they are really strong one, like autonomous weapons will become the Kalashnikov of tomorrow's. They require no costly and hard to obtain raw materials. Ideal for tasks such as assassination, destabilizing nations, selectively killing a particular ethnic group. Should be prevented by a ban on offensive autonomous weapons beyond meaningful human control. That's not science fiction authors, that's a letter of people who work on it to politicians. There are more than 20,000 signatories, like Stuart Russell, Stephen Hawking, Elon Musk, Steve Wozniak, etc. So that's something that we should really care if the experts say so. The same year, these Bilderberg meetings, you know this? This Bilderberg group is something, sometimes, if you believe in this conspiracy, terrorists, and etc., it's sometimes called a world government, because these are meetings for top politicians, businessmen, business people of the world. Presidents of biggest countries discuss some topics with the richest people in the world, the CEOs of the biggest companies, right? That's why many people are really afraid of this. So, and also these meetings are mostly confidential, so it's not really announced what was discussed there. But every year, the agenda is officially published, so you can at least check the topics which were discussed by these people, like the most powerful people in the world. And the number one on this checklist is artificial intelligence. Like, you see, that's the topic discussed by the people that can influence our future most. So maybe they know something. We'll learn soon, right? How far we are really from this AI to become a strong one, right? If the most powerful people discuss this topic, maybe it's worth to have a while and think about this on our side too. At the same year, we have this OpenAI with $1 billion endowment, with some mission as a non-profit artificial intelligence research company, build safe AI, and AI benefits are widely and evenly distributed as possible, right? Musk, Altman, and others. $1 billion invest. Why? Maybe because it's important. Maybe it's because it's really our future, and we should accept this. September this year, this huge partnership on AI. Have you heard this? Partnership: Amazon, Facebook, Google, Microsoft, IBM. The most powerful companies in the world. They join their knowledge, join their goals to build and improve artificial intelligence. I believe it's only the case of time. Future. So usually when we think about the future, there are like happy path or the bad one. So the bad one is like everything we can see in these science fiction movies, like direct attacks, like Skynet from the Terminator movies. We have this direct imprisonment, like Matrix movie. But we can also imagine some indirect one, like there will be so many life restrictions that our life become stop interesting anymore, right? So AI can control us for our safety, but it can be too much control in there, right? Finally, AI as humans can make a mistake with some global consequences, right? Like stock market crash or destruction of all food suppliers. So it's not only direct and direct attack. There are many other reasons why we should be careful with artificial intelligence. Of course, on the other side, we have this happy path, like no hunger, no illness, no poverty, no money, actually, because we don't need it, because we have everything distributed for free. Free time, long life. So it sounds perfectly. I believe whenever this topic is discussed, we forgot about this third aspect. I mean, would actually we, humans, will be ready for life without any social divisions, fear, money, and unfulfilled dreams, right? We may be the weakest part in this future, right? If we have everything, are we ready for this, actually? For such a life? And with this question, I wanted to leave you. Here are my contact details. Don't forget to start following me on Twitter, dr_Hawaii. I tweet about artificial intelligence, IT, and also positive thinking, because after all, I still believe our future is much brighter than we really expect. And I think it's a very nice sentence to end this talk. Thank you.